is represent y, so that's your y-axis. Okay. So you take the ln value of all your k values and put them on the y-axis. EA over R becomes your slope. 1 over t is your x-axis, and ln of A is your y-intercept. So this is y, this is m, this is your x-axis, and this is your y-intercept. So where it cuts the y-axis, that's the value of ln of A. For example, so we all agree that this is y. So basically, you just take any 2 points in the graph and find the slope of the reaction. Find the slope. So you have let's use these 2 points. Well, it's gonna be hard to. Okay, so we have these 2 points here. It's gonna be hard to take an accurate value of this.
Yeah.
But we can try. Okay, so we got any 2 points in the graph. This can be our x1, this can be the x2, then this to be y1, and this to be y2. Okay, so you know that the formula for slope is y2 minus y1 over x2 minus x1?
Yes.
Cool. Alright, so what's the value for y2?
Would it be like negative 10?
Yeah, we don't have to use the accurate numbers, but yeah.
Y wouldn't be, can I say like negative 8 point, wait.
You can do 7.5, negative 7.5.
7.5, okay. So this one, like, we're kind of reading it, like, backward, okay?
Yes.
Okay.
This is negative 5, 6, 7. The 8 point would be around here.
Okay. Gotcha. X2.
So x2.
1.5, can I say?
You can use 0.021.
Okay.
Again, it doesn't have to be accurate. Yeah, if she gives you this on the exam, it'll be much simpler to read.
Did you get negative 25000?
Let's see. Negative 25,000?
Yes.
Okay, so this value is equal to negative EA over R, right? So that is our slope of the graph.
Okay. So we didn't need to do like the temperature or like put like R in it?
Exactly, we don't need to do that because that's already our x-axis.
Okay.
And the k is already our y-axis.
Okay.
So the slope of the graph is equal to negative EA over R. Okay? So since we know that R is a constant, right?
Yes.
So we can use this to find the activation energy for the reaction.
Okay.
So we can do negative 25,000 is equal to negative EA over the R is 8.314, I believe. Yeah. It's 8.314.
Is A, is this one like in the joules form?
Yes, that's joules per mole per Kelvin.
Okay.
Yes, I don't think you use the other one for this. Okay. So EA becomes 25,000 times 8.314. And that'll give us the activation energy in joules.
203,350.
Okay.
Oh wait, did it wrong.
That's what I got.
203. Okay, yes, I got it wrong. I accidentally put it 134. That's
Oh, I see.
4.
Okay, cool. Yeah, so that's how you can use a graph.
Okay.
Yeah, and where it crosses the y-axis will be your frequency factor. So I guess like if this graph were to extend past the y-axis here, your y-intercept.
Yeah.
So that value is equal to ln of a.
Oh, right.
Okay. So your a is, I believe, is frequency factor. Okay. So you can say, let me say that number is negative 5.5.
Yep.
So you have that ln of a is equal to negative 5.5.
Okay.
Then a will be equal to what?
Is that where we do the e?
Yes, e to negative 5.5.
It'll be like
Put that in your calculator and that will give you the value of a.
0.0040.
Cool.
You can round.
No, that's what a is.
Okay.
Your slope is equal to negative EA over R, and your y-intercept is equal to ln of a.
Okay.
So those are the kinds of things she might ask you if she gave you a graph for this.
Okay.
Let's see some questions. So how do you study for this class?
I look at kind of her examples. I kind of go back to it and look at it and try to do them myself. And I'm gonna try the practice test, or very the same thing. But I guess it's like some kind of practice. Yeah. Do you have like any recommendation on how to kind of review for this?
I would do the practice problems at the end of the chapter. Do you have the textbook for this class?
Yes.
Okay, yeah. So usually at the end of the chapter they have like practice problems there. Okay, so just to make sure that you have this down pat. So if there's any one that you're stuck on, then we can go over that during our tutoring sessions. Yeah. But what we went over, did it make sense?
Yes. Because I was having trouble kind of like understanding behind something. She didn't really show it to us.
Oh, really? Wow.
And I was kind of scared to ask her questions. Yeah, I don't know if it's gonna make sense or not.
Okay, let me see. I have some questions I can send you. Would you like to meet tomorrow again?
Not sure yet.
Okay.
I can try. Is it fine?
Because we only met for 40 minutes today, and we're done with what you had sent me earlier. Do you have any more questions that you wanted to go over?
I think I have a question based on catalyzed and versus uncatalyzed reactions.
Okay.
That one. But I don't have like any examples. I think I'm trying to understand like the concept behind it.
Okay. Let me see what's going on. So basically, a catalyst speeds up a reaction, but it's not used up during the reaction. So at the end of the reaction, after you form your product, you will still find a catalyst present. Okay, so where is it? A catalyst. Oh, they talk about enzymes here. Oh, I really just messed it. Okay, so a catalyst speeds up the reaction by decreasing the activation energy. So, for example, do you see this graph over here?
Yes.
Yes. So, yeah. So the presence and the absence of a catalyst, which is the blue graph, the activation energy is much higher than in the presence of a catalyst, which is the red graph.
So the catalyst is on the bottom, the uncatalyst is on top?
Yes.
Okay.
Yes. So the uncatalyzed reaction is the blue, the one in blue,
Okay.
and the catalyzed reaction is the red line.
The red line, okay.
Okay? So you see that the uncatalyzed reaction has a higher activation energy than the catalyzed reaction. The activation energy is the peak of the graph.
Oh, okay.
So the peak of the graph minus the reactance. So the distance between the peak of the graph and the reactance is your activation energy.
Oh, okay.
Okay? So the activation energy is sort of like the barrier that the reactants have to cross before it gets to the product. So the higher the activation energy, the slower the reaction.
Oh, higher the activation energy?
Yes, that's what it's called, activation energy.
The slower
The reaction.
the reaction. Okay. So like based on this graph, the uncatalyzed one has that higher
Activation energy. Yes.
Okay, so that's why it's slower. Okay.
Yes. So think of activation energy like a wall, like a wall that you have to climb, right? The higher the wall, the slower it is to get to the other side, right?
Yeah.
Yeah. So that's what a catalyst does. It lowers that activation energy, making the reaction faster.
Oh, okay.
Yeah. That's pretty much all it does.
Okay. Cool.
And there's things like homogeneous and heterogeneous catalysts. Homogeneous catalyst is like it's in the same phase as the reactants. For example, if your reactants are gases, then if your catalyst is a gas, it's a homogeneous catalyst. If all your reactants are gases and your catalyst is a solid, then it's a heterogeneous catalyst.
Can you say that one more time?
Okay. So homogeneous catalyst is a catalyst in the same phase as the reactants. Okay? So that means that if your reactants are gases, right, a homogeneous catalyst will also be a gas. If your reactants are solids, your homogeneous catalyst will also be a solid. Okay? Now, heterogeneous means that they are in different phases. For example, if your reactants are gases and your catalyst is a solid, then that will make it a heterogeneous catalyst, which is this one here. So you can see from the picture that your reactants are gases, right? And your catalyst is a solid. The one in yellow is a catalyst.
So the bottom is that catalyst, and the ones that the gases, they're just
They're farther apart, right?
Yes.
Yes. The solids are tightly packed.
Okay.
Yeah. So if you look at the picture on the left, the catalyst is also a gas.
Okay. This makes much sense.
I don't see any question that you can ask in catalysis.
Yeah.
I mean, other than what does a catalyst do?
Yeah.
but there's no math associated with catalysis. I mean, you can send me your PowerPoint so I can make sure that we've gone over everything that needs to be gone over.
Okay.
But I'm about to send you, these are like some practice questions that you can try on your own to make sure that you have a good understanding of the material. But I would suggest doing the ones in your textbook first.
Okay.
Yeah, so once you try those ones, you can send me your answers. And if there's anyone that you're not able to answer, then we can go over, those ones together.
Okay.
Yeah. But then if you're done with the one in the textbook, then I can send you these for extra practice if you need it.
Oh, okay. Okay. That sounds good.
What is the name of your textbook?
I'm not exactly sure.
It seems like you guys don't use it at all.
Yeah, we don't even use it. It's the Smart Work one, not a textbook.
Do you? What was I gonna ask? Like, does she give you guys worksheets that she can do, or?
Oh, yes.
She does?
She does have like the content right, the D2L.
Okay.
And so,
Can I see that?
yeah.
You can open it and show your screen so I can see it. Stop sharing.
Something like this. Do I just press the green one to share the screen?
Huh?
Do I share screen?
Yeah, you can.
Okay.
Should be able to. Yes. Oh, there we go.
I think I also screenshot some of this too.
Oh, I see.
Mm-hmm.
Calculate the work constants for the following reactions, for the two reactions below A and B. Okay, so she gives you A, she's giving me EA. What is the temperature? Oh wait, what formula is it supposed to use now?
Isn't that the K one?
But she needs temperature though.
Temperature.
Right, unless she's assuming that it's room temperature.
Is let's say is the room temperature what number would room temperature be? Would it be
That's 25 degrees Celsius or 298 Kelvin.
Okay.
Yes. But it has to be temperature there for you to be able to do this.
Yeah. I can also email her just in case about it too, with what she needs.
Okay.
I'm gonna try to do these two.
So we've done 5 as well. Okay. We've done 5. So number 6, consider the graph below. Okay. Calculate the activation energy. So we did that already.
Yeah.
What is the rate constant for the reaction when the temperature is 400 Kelvin? So you do 1 over 400 Kelvin. Because you know that the x-axis is 1 over t. Right? Yeah. So you do 1 over 400 and see what that gives you.
Okay. 0.0025.
Oh, never mind that. Let's see. What would you do? You would have to do. You'd have to find the equation for this reaction. For this graph. Again, it's not going to be super accurate, but you can try.
Okay.
Oh, she gives you 2 points that you can use on the graph already. You see those lines that she has on there?
Yes.
Yes. So those are 2 points that you can use to solve for your.
The slope level?
Yes. So you can solve for the slope, and then you can also we already approximated what the A value is going to be. Okay. So I guess I can stop sharing this. Do you have an idea how you're going to solve the B part of this?
Not sure yet. I don't have it.
Okay, that's fine. Okay, I got to stop sharing this. You can stop sharing this and I'll share my screen.
Okay.
So basically you just get an equation in this form, y equals mx plus b.
Okay.
Right? So y is this. So y, we know that is ln of k. So what was the slope of this graph when we calculated it first?
The slope of which one?
The slope of the graph was negative 25,000, right?
Yes.
So that's what I'm going to put over here, negative 25,000. Then I'm going to put x, and the slope of my graph was about, again, is going to be about 5.5. So this is our equation for the graph.
Oh.
So the slope was what we calculated over here to be 25,000.
Mm-hmm.
So we're using the format equals y equals ms plus b.
Okay.
So m represents the slope, which is 25,000.
Mm-hmm.
Okay. And then we had b, which was 5.5. Remember, b was the y-intercept.
Okay. Oh,
So where it cuts the graph over here, that's our y. That's our y-intercept, or b value.
Okay.
So that was what I put there. So this would be the equation for the graph. Okay. Now she's asking about the the k value if the temperature is 400 Kelvin. So you're going to do 25,000 times 1 over 400. Because remember, x is equal to 1 over t.
Yes.
Okay? Plus 5.5. And that will give you the value for y. Okay?
What was
So we can put
y again?
y is equal to ln of k.
ln of k. Okay.
Okay? So when you find the y value, then you can find k.
Okay. Negative 57.
So 2,500 divided by 400. Okay, so negative is 5.5. Yes, so y equals negative 57. So this is also equal to ln of k, right?
Yes.
So what is the value for k?
Okay. 1.75 e times 10 to the negative 25.
So ln of k is just negative, is equal to e to the power of negative 57.
Yeah. And then I got 1.75 e and then to the negative 25.
Oh, okay. This?
25.
25.
Yes.
Okay.
25. That's correct.
Yeah. That's it.
Okay.
Do you think you can do something like this by yourself?
Yes. I'm gonna try.
So you can send me pictures of the problems that you decide to solve from the textbook.
Okay.
And it doesn't have to be too many. Just I don't know what the textbook looks like, but maybe you can pick 2 problems from each topic under this chapter, and then just try those and see how far you're able to get.
Okay. Yeah, I'll try that.
Okay, cool. You have any homework due for this class?
It's gonna be due on Friday.
Okay, so you did that already.
Yes.
Okay, how did that go?
I think it went good.
Okay.
And we're gonna have another homework due soon. I think I'm gonna try that one too.
Okay. That's on the kinetics?
I think so.
Okay.
With the mechanism as well.
Okay. Yeah. So we can do that. And do you have any other questions regarding?
No questions yet.
Okay. Yeah. Again, anytime you want to meet next week is up to you. We don't have to meet on Saturdays.
Okay.
But anytime that works best for you. then we can schedule something.
Sure thing. Okay.
Okay. All right, you're doing great. So practice those questions, and do you think you'll be able to do some by Monday?
Yes.
Okay, cool. So Monday evening, you send me the ones that you've answered and your answers to them.
Okay.
Okay.
Cool thing.
Good. Great job, Stephanie.
Thank you, Lauren. Thank you for helping me and clarifying everything for me. I appreciate it.
No problem. Okay. Have a good day, okay?
You too.
Bye.
Bye, Lauren.